Uh, Hi, my name is Dana Golden. So a little bit about me. I'm a third, soon to be fourth year PhD student in economics at Stony Brook. I have master's degrees in economics and analytics with a concentration in machine learning. I worked as an economist for the USDA and the Federal Energy Regulatory Commission and as a data scientist for Treasury. My research focuses on the economics of electricity markets and energy transition. Happy to chat about anything related to economics and data science, as well as natural language processing, computer vision, deep learning, and reinforcement learning. My office hours are on Zoom and in person at my office. That's S630, 3:30 to 5:30 Monday, 8 to 10 a.m. Friday, and 11 a.m. Tuesday. These might have changed some, but go with what's on the syllabus, not what's right here. To overview the course, this is a really great introduction to machine learning and the associated mathematical and coding techniques. We'll start with the basics: optimization, gradient descent, Newton's method. We'll go through linear algebra, linear regression from machine learning perspective. We'll go on to dimensionality reduction. We'll talk about supervised, unsupervised learning, large-scale machine learning, and reinforcement learning. Grades will be based on participation, problem sets, 2 midterms, and a final. And problem sets will be in Python. A test will be either proctored online or proctored in person. If you want to do an in-person exam, I actually let me know if you have a strong bias towards in-person, and I can see if we can set that up. Most of you will be doing the default will be online. It'll be assumed they'll be doing online, but email me if you have some reason why online just would not work out for you. So I plan for recitations, and when this class was conceived, the recitations, this right here, was not really in the plans. The reason it was added, and this was a late addition, is because, and ignore this 8 to 10 a.m. Thursdays, we decided to just move to one recitation. But the reason it was added was because coding is not a spectator sport, and learning is not a spectator sport. And it's really valuable to have the coding demonstrations and the math demonstrations here. I encourage you to, while you're here, get out pen, paper. If we're working through any math, work through the math together. And also, any code that I work through, I encourage you to run on your personal machine. It's very valuable to run code and to figure out what's working, what's not working, while things are going on. Encourage you also to work practice problems and, we're going to work practice problems together. We're going to do coding demonstrations. I'm going to answer questions from students. If you have any questions that you want reviewed, send it beforehand and we can talk about it. Is there anything else anyone would really want out of this recitation? This is your time. I am trying to do this to really make this experience more productive for you guys. All right, seeing nothing. So machine learning, broadly speaking, there are a few different ways to think about machine learning. The first would be that it's a rebranding of classical statistics. The second would be that it's a very different way to think about statistics that takes advantage of old techniques with new tools that we have. We have a great increase in data. We have a great increase in computational tools, and these together have combined to create a situation wherein it makes sense to utilize different statistical techniques than in the past. So machine learning, broadly speaking, has three separate separate bubbles, which everything comes in. The first is supervised learning, the second is unsupervised learning, the third is reinforcement learning. Supervised learning means that you're giving the algorithm the answer. This is linear regression. This is classification. You have some data points you know the answer for. You have some data points you don't, but you're trying to learn the relationship between X and Y. Unsupervised learning, you don't necessarily know the answer, but you're trying to find patterns in your data. This is principal component analysis. This is support vector machines. Actually, support vector machines would not go under here. I meant to say this is clustering. This is k-means. And then finally, so that you're just finding patterns in the data. And then reinforcement learning is fundamentally very different. It focuses on learning about the environment by giving rewards and punishments to an agent. Reinforcement learning is actually very similar in kind to the kind of problems you solve in economics. So how machine learning is used in economics? You can create quick classifiers of unstructured data. You might want to group a bunch of data points into particular bins. You might need to work with text or image data. You might have a prediction task or need to sort through variables. So maybe you need to predict an outcome, or you have a bunch of variables you need to go through to fewer, and then you might want to solve value iterations problems of deep learning. That's a recent application of machine learning, and it seems to be very, very powerful. Potential for great growth over time. And yeah, a question that I think is important to address is, we're economists. Economists are not the best programmers, so why hire them to do machine learning? Economists know data. Economists have a real comparative advantage in data and dealing with the kind of data you deal with in the real world. In the real world, you don't often get nice data sets you'll find in this class, you'll find in other classes. You often get data sets that require a lot of cleaning and require you to think very hard about what the assumptions of the data set are. So you have to work to put together the data set. You also have to think about, what assumptions am I making by using this data set? Economists know the theories that allow them to make sense of the data. Economists have thoughts on why Y causes X and don't just run a bunch of regressions. Economists know causality. Economists have a rigorous approach to statistics missing from machine learning. A lot of times machine learning just focuses on running a bunch of regressions and finding ways to predict things. It doesn't think really hard about the statistics, but that's something you and I are trained really well to do. In a lot of ways, machine learning is a rebranding of econometrics and classical statistics. But machine learning focuses on prediction and implementability, where economists care about causality and statistical rigor. That's why it's really hard to publish machine learning papers in economics, because it's really hard to draw causality from economics or from machine learning. You really need in economics to know why things are happening, be able to connect phenomena. Many economic models have analytical solutions. And what this means is that you really can find the answer through doing a bunch of math in economics quite often. But in machine learning, you generally are not going to have an analytical solution. You're going to have to settle for an imperfect solution that comes from iteration. Some common terminology: loss and cost function. This is the objective function to be optimized during training. In economics, we talk about least squared regression, or sum of squared errors. In that case, squared error is the cost function. So in linear regression, we think of the cost function as squared error. Train, test, split. Before training a model in machine learning, we hold out some of the data for testing. We want to see how well our model works on data it hasn't seen before. And so this is a question for all of you. Economists don't do this. Almost never do economists do this. So why do machine learning people? What are some thoughts you might have on this? Jason? Why would you want to split your data? Why wouldn't you want to train on all of your data? Anyone have any thoughts?
Uh, is it because it can be faster to train in less data?
Could you repeat that? I'm sorry, I didn't hear you.
Is it because it can be faster to train an algorithm in less data?
So that's one reason. That's not the main reason we do it. That's a good idea. It is faster to train on less data, but why might it be good to test your algorithm? So when you're creating an algorithm, when you're creating a model, you don't necessarily know how well it works. You don't necessarily know if it works. So by creating a test set, you're verifying that it's not really working really well on your training data and then not working well on data it hasn't seen. So this is what deals with what's called the overfitting problem. Overfitting is when a model is too complex and fits its training data better than its test data. So you don't want a model that's perfectly fit to the data you show it and then doesn't work on data you don't show it. You want a model that works well even on data it's never seen before. So in economics, we have these ideas of bias and variance. So the bias of a model is how wrong we can expect it to be, and the variance of a model is how unpredicted you can expect it to be. It's a very similar to the ideas of precision and accuracy. So the right estimator contains the optimal amount of bias plus variance. So we'll talk about that later on in the course. And cross-validation is the process of finding parameters for the model using a subset of training data. So are there any questions on that broad overview of the course before we get into some practice? Any questions so far? All right, we're going to start off pretty easy. I'm sure some of you are going to be bored, maybe all of you, with some partial derivatives. So if we're going to take the derivative df of x, y, dx, what would that be? So how would I go about doing this? So how does a partial, what's the trick to doing a partial derivative? Yeah, 2xy, exactly. So the trick to doing a partial derivative is you hold one variable constant while moving the other variable. So now if I want to do df of xy dy, what would that be now? So remember, we're holding x constant while allowing y to move. So we're holding y constant while allowing x to move. Yep, x squared plus 3y squared. Excellent. So now gradient represents the vector derivative of a function. So this is a derivative with respect to all directions simultaneously. So the gradient here is dg over dx dg over dy, dg over dz. So the gradient, the reason why we're talking about it is because it's very important for optimization. You're often going to do a thing called gradient and descent, where you have to optimize a function by finding the derivative with respect to all directions, and you're going to try to move down the hill with respect to the gradient. So what would dg dx be here? And what would dg dy be here? And then what would dg dz be here? So e to the yz, and then xz e to the xz, and xy e to the yz. And so there you have basically a derivative in all directions for what's called the gradients. Lagrangian optimization is a technique for optimizing a multivariate function subject to constraints. So given the following function, find and constraints, find critical points. For those of you who are who've taken intermediate micro, this will be a very quick review for you. It's a very simple thing. So we have the function 3x squared plus 2xy. Three x squared plus 2xy plus y squared subject to x plus y equals 1. And then if we want to solve this as Lagrangian, we do big L Lagrangian equals 3x squared plus 2xy plus y squared plus lambda 1 minus x minus y. And then what's the next step we do when solving this? What's the next step we have to do? So we take the partial derivatives with respect to y and with respect to x and with respect to lambda. And then what do we do with those partial derivatives? So remember, we're optimizing a function. So what do you do with partial derivatives when you optimize a function? Anyone? Not initial guesses. That's a great answer for computer science and for this class. Yeah, a lot of times we would be using an initial guess. In this case, though, what we want to do is set the derivative equal to 0. So you're very close. In this case, though, we're setting the derivative equal to 0. So 6x plus 2y plus 2y plus, and then we take the derivative with respect to x. So negative lambda equals 0. All right. And then 2x plus 2y minus lambda equals 0. And then dl d lambda equals 1 minus x minus y equals 0. Now, what do you think we should do next? Does anyone have a thought as to what we should do next? So we're solving a system of equations. I got suggest here. Yeah, solve all three of the system of equations. Exactly. We're solving all three of a system of equations. So when you're solving a system of equations, the first step is generally to solve for one of the variables. So which variable do you think we should solve for? There's almost always in economics, when you're doing a Lagrangian optimization, there's one variable you solve for first. Does anyone remember what it is? It's really low-hanging fruit in this problem. It's lambda. So we're gonna put the first two equations in terms of lambda. Lambda equals 6x plus 2y plus 2y. I should probably have made that 4y. Lambda equals 2x plus 2y plus 2y. So it's 2y. So I'm just gonna write this mistake and plus 4y. All right. So now, what do you want to do with these two equations in terms of lambda? We have two equations in terms of lambda. What do you want to do with them? Got some answers up here. Set them equal to each other. Great job, Basim. Great job, MD. I don't know if I said your name right. Please correct me if I did not, as I don't think I did. 4y equals 2x plus 2y. And then now 4x equals negative 2y. X equals negative 1 over 2y. Yeah, you did as in I said it correctly, or yeah, you did as I mispronounced it. Just let me know the correct pronunciation if when you can. Cool. 1 minus x minus y equals 0. So 1 minus x minus y equals 0. And x equals negative 1/2 y. So what we're going to do is we're going to substitute this in. 1 minus 1/2 y minus y equals 0. And then 1 minus 3/2 y equals 0. Y equals negative 3/2 y equals negative 1. Y equals 3/2. All right, so y equals 2/3. And then we know that 1 minus x minus y equals 0. So 1 minus x minus 2/3 equals 0. 1/3 minus x equals 0. X equals 1 out of 3. And now we've solved for the optimum in our problem, given the constraints. I'll also say with a equation like this, there's something else we'd have to do to know whether or not it's a minimum or a maximum. So when you have found the critical points, what do you have to do to figure out whether or not it's a minimum or a maximum? And we also don't yet know whether or not it's a global minimum or maximum. So there's something else we'd have to do. This actually is just a candidate point. So something else we'd have to do. What would we have to do? There's a kind of test we need to perform. That's right, the second derivative test. So in real life, we would take the second derivative, find out where the function is increasing, find out where the function is decreasing, and then we would figure out what type of points we have. We're not going to do that today, but just a good thing to always keep in mind. So chain rule. The chain rule is at the bedrock of optimization. And if any of you ever do anything serious with neural nets, much more serious than we'll do in this class, you will live and die by your application of chain rule. Chain rule is foundational to neural networks in every sense of the word. So basically the idea of chain rule is that you find a derivative of a function by finding the derivatives of that function with respect to another function, and then finding the derivative of that function with respect to the variable you're interested in. That was kind of a mouthful. So f of u comma v over dx equals f of u comma v du times f of u comma v over dv or over dx, or sorry, times f of u, or sorry, let me start over. That was a bad way of doing that. Sorry about that. F of u comma v over dx equals f of uv over du over dx plus f of u comma v dv dx. And then y is basically the same thing over dy dy. All right. So what is f of u comma v d? What is f of u comma v du? Df, yeah, over du equals 2u, df over dv equals 2v, and then du dx equals 1, du over dy equals 1, dv over dx equals 1, dv over dy equals -1. So putting that all together, 2u times 1 equals df over dx, and then 2 or plus 2v times 1. Let me clear this all up before I do this. Df over dx equals 2u times 1 plus 2v times 1. Df over dy equals 2u times 1 plus 2v times -1. And then what's the last step to fully solve this problem? What do we have to substitute in for what? We have to substitute in x plus y for u and x minus y for v. All right. So I'm not going to solve with the Hessian matrix here, but actually I will solve with the Hessian matrix here. The Hessian matrix is a matrix of second derivatives, very important for maximizing things and finding the minimums. Its second derivative test is very important. So to find the Hessian, first off we find the Jacobian. So the Jacobian is just the derivative of the function with respect to x, and then the derivative of the function with respect to y. So that's 12x squared plus 2y, and then 2x plus 2y. And then to find the Hessian, we take the second derivative with respect to y, and then the mixed partial derivatives, and then the second derivative with respect to x. So the second derivative with respect to x is 24 x y. Second derivative with respect to y is 2. And then the mixed partial derivative, we take the derivative of the first and the derivative of the second, first with respect to x, and the derivative of the second with respect to y. Important property of these is that they should be equal under certain conditions. So derivative of the first with respect to y, 12x squared plus 2. I don't think this met the conditions for them to be equal. Derivative of the second with respect to x, this is just 2. All right. So that's a Hessian matrix, very important in optimization. So some basic probability concepts. We're just going to do some math right now before we get into the Python. I know that's what you're all excited to see. You have expected value. The expected value is equal to the value of a variable times its probability summed up. So that's only the expected value when we're talking about things that are discrete. When we're talking about things that are conditional, what would the expected value be? Anyone have any thoughts? It would be integral from -infinity. Yeah. The mean. So yeah, the mean. But how do we calculate the mean for something that's continuous? Integral from -infinity to infinity of f of x times x dx. And that is expected value of x. So you can find the mean of a continuous variable by taking the integral over its support time of the probability density function. I remember that continuous variables are probability density functions, discrete variables are probability mass functions, and then times itself. The variance of a variable. So there are two different definitions of variance. One is the expected value of x squared minus the expected value of x squared. Here's an interesting question that I love asking. So variance can never ever be negative. So what is the mathematical property that makes expected value of x squared minus expected value of x squared always positive? So this isn't true for all. This is not true for all data. This is not true for all functions generally, but it is true for all functions that are probability functions, because probability functions have a special property. Does anyone know what this property is? I'll give you a clue. The inequality that this is based on is called Jensen's inequality. So what property of probability density functions makes the variance always positive? It's a very important property when we're talking about economics. What's the shape of a production possibility curve? So concavity. Concavity is a property because probability density functions are concave, and because and also because the square is a concave function, the expected value of x squared will always be greater than the expected value of x squared, leading to positive variances. Similarly, you can also take the variance by taking all of the individual data points and subtracting the mean, and then dividing by the number of data points. Variance is often called the second moment, or the second moment. The mean is the first moment. Correlation coefficient is the covariance of x and y, which is equal to expected value of xy minus expected value of x times the expected value of y. Will this always be positive? Will the covariance of two variables always be positive, like the variance? No. Covariances are not generally positive. In fact, there are plenty of situations where the covariance will not be positive. So the correlation coefficient is the covariance of xy divided by the square root of the variance of x times the variance of y, or this other function over here, which is for data points. And then if two variables are independent, the expected value of x times y is equal to the expected value of x times the expected value of y. If two variables are independent, this also implies that the PDF of x times PDF of y is equal to the PDF of x comma y. If I'm losing anyone, or if I'm going too slow, feel free to ask any questions at any time, get clarification, or just tell me, look, Dana, this is all very introductory. You need to speed up. All right. So, and this is kind of an introductory week. So, you know, hopefully hopefully it is a little bit boring because, you know, you've come through all these other courses and you've learned your stuff. Let x1 and x2 be independent continuous random variables uniformly distributed from 0 to 1, and let x equal the max of x1 and 2x2. Find E of x, find var of x, and find covar of x1, x2. So first off, what is the... you all can see my OneNote, right? Great. So what is the probability density function of a uniform random variable from 0 to 1? U of 0 comma 1. Does anyone remember from basic probability what the PDF of that is? So the PDF of a uniform distribution is 1 over A minus B, distributed A comma B, 1 over A minus B. So the PDF of a uniform distribution is just 1 over 1 minus 0, or 1. All right? And so seem to have accidentally gone back to the beginning. It's not great. So the expected value of a variable, we said it before, trying to find max of A comma B. The expected value of a random variable is integral from negative infinity to infinity, or in this case, what is the support of the random variable? The support in this case is not negative infinity to infinity. The support in this case is actually 0 to 1. The support in this case is 0 to 1. So in this case, what we do is we do integral. We're taking a double integral, and we're taking the max of two variables. So max of x1 and x2. So we take integral xy times f of x comma y. And then now the real trick here is that we have to make a change to the support. Does anyone know what the change to the support you have to do to solve this problem is? So support is the bounds of the integral. So it's a max function. So instead of integrating from 0 to 1, we'll actually integrate this from x to 1, and then from 0 to 1. So we integrate from oh, sorry, not from x to, because we have defined it as 2x. In actuality, we have to integrate from we integrate from 2x to 1, and then from 0 to 1, dx dy. So if we integrate this out, and then what is f of xy? F of xy is what? 1. So integral of 2x to 1, integral 0 to 1, xy times dx dy. And that just goes to, this should be dy dx. Sorry about that. Dy dx. That goes to x squared, 1 half x squared. Messed up again. I took the integral of x first. This goes to x y squared, 1 half xy squared, from 2x to 1. And then we plug those in, and we get 1 half times 2x squared times x equals 2x cubed minus, and then, or sorry, minus that is, so, and then we evaluate this at 1, so 1 half x minus 1 half, or minus 2x cubed. And then we integrate this times y. Not times y. We put in text y. We integrate this from 0 to 1 dx, and this goes to 1/2 x squared, 1/4 x squared minus 2 out of 4 x to the 4th. And at 1, this becomes 1/4 minus 1/2. And at 0, this becomes 0. So this becomes negative 1/2 plus negative 1. Oh, sorry. Yeah, 0 minus negative 1/2. There we go. 0 minus negative 1/2 equals 1/2. So this becomes 1/2. So that's the expected value of x. If we want to find the variance of x, we would do the same, but for x squared, and then we would subtract the expected value of x squared, or we would subtract the expected value of x squared from the expected value of x squared, and then find the covariance. We would find the expected value of x times y, and then subtract the expected value of x times the expected value of y. I'm going to skip the rest of the probability section with respect to time. I'm going to go on real quick through the stats overview, and then we're going to get to the review of Python, which is the real meat of today's lesson. Maximum likelihood estimators maximize the probability of an estimator. So you find the analytical maximum or the applied maximum of a estimator in an MLE. You do this in IID distributions by multiplying, and the logarithm is taken, and then the maximum is found. Why, when we're doing maximum likelihood estimation, do we take the logarithm? What's useful about the logarithm when you're multiplying things? So the logarithm of 2, so the log of xy equals log of x plus log y. This, of course, is a very valuable property that the logarithm of 2 variables multiplied is the sum of the logs. And so this means that instead of having to take the maximum, take the derivative of a bunch of variables multiplied together, you just have to take the derivative of a sum of variables. This makes it a lot easier, and this works because the maximum of the logarithm of a variable is equal to the maximum of that variable. Or sorry, not the maximum. Yeah, the value of the variable that maximizes the function is the same whether or not you take the log of it, because log is a homogeneous function. This makes the most assumption about distributions, and it's a consistent but efficient, but not certain to be unbiased. So there are certain situations where maximum likelihood estimators are biased and makes the most assumptions. But what is the real benefit of an MLE? Why do we like maximum likelihood estimators? Why are they so ubiquitous throughout statistics? So maximum likelihood estimators make the most assumptions, but they're also the most efficient. So if you're taking them right, they'll converge to the right answer a lot faster, which makes them very valuable if you have smaller samples in terms of data, and just makes them easier to work with often, just in general. This is OLS via ML. I think I'll show this a couple times throughout the course. We'll dig into it later on, but basically you have a likelihood function, which is you have this error. The error is assumed to be normal 0 sigma squared. And then u can be solved for as u equals y minus x beta. And then if you have normal sigma squared, 0 sigma squared as the function, you can plug in y minus x beta as your operator you're minimizing, and then you're maximizing, rather, because maximum likelihood. You can plug in y minus x beta as the operator you're maximizing, and then you just take the logarithm, and so that moves the exponential to just normal function, and then you have the sum of 2 pi, and that goes to 0 when you take the derivative, and then you have an ln of sigma. We're not worrying about sigma right now. We're only trying to solve for beta. We're trying to find the estimator of beta. And then when you take the derivative of this log likelihood function with respect to beta, what happens? Does anyone know what happens when you take the derivative of this with respect to beta? Let's take it. We've got time. dl over d beta. What are we minimizing is this should still be squared. dl over d beta, we're minimizing the sum of squared errors. So when we solve this, we're solving for the value that minimizes the sum of squared errors, which is equivalent to the least squares linear regression estimator. So an alternative to a maximum likelihood estimator, and the less common one in this class, is a method of moments estimator. These ones use the empirical moments as the true moments and solve for estimators that minimize the difference. Method of moments estimators make fewer assumptions. They're unbiased, but generally less efficient. They're kind of a little bit more brute as a way of doing it. But basically, this involves taking the mean of the data as the expected value of the data and then solving for your estimator. So some terms I've been using: unbiased estimators have an expectation that is asymptotically equal to the true value. Consistent estimators converge probabilistically to the true value. So unbiased estimators, you expect them to be right even with low numbers of samples. Consistent estimators, you expect them to be right if you have enough samples. So unbiased is a small sample property. Consistency is a large sample property. So that's going to be the first PowerPoint for tonight. Now we're going to go on to the Python review, Python intro/review. Does anyone have any questions so far? And this is very important that everyone answers this. Does anyone not have Python installed on the machine they're currently working on? So I'm going to take that as a sign that you all do, and you can all run the code I'm about to show you on your personal machines. But just assuming that you can't, I'm going to show you right now a really great tool. So if you search for Google Colab, it will come right up as that first link there. And basically, Google Colab is what's called a Jupyter notebook. And we'll talk about what Jupyter notebooks are in a few minutes. But Jupyter notebooks allow you to interact with Python in a much easier way than you would normally interact with Python. The traditional way to interact with Python, the way I interact with Python, is through the command line. I type things in and then I run them in the command line. The way that you interact with Python now, and the better way to interact with Python now, I would say, is through Jupyter Notebook. So here you have a much more modular version of the code where you can just run bits and pieces at a time, and it's a lot more readable than you would generally. And this is very valuable. Google Colab is a valuable resource because you don't really have to have Python installed on the machine that you're running it on. But more importantly, it can easily be shared with other collaborators, so you don't have to go through a software like Git. And also, Google Colab is a very easy way of accessing GPU power. So if you're ever like, I want GPU power, but I don't have access to it because I'm poor, and I go to Stony Brook, and Stony Brook is poor, and we're all poor. Then you could be like, oh, but I have access to Google Colab, and then I can just use their GPU power and run things. It's great. It really is great. It's the best. So what is Python? Python is a general purpose, object-oriented, high-level programming language. It's very useful for rapid application development and quick scripting. It is a quick edit debug cycle that makes extremely high productivity, and as an incredibly active programming community, this makes it really easy to find solutions to the problem you're solving. And it also means that when things come out, when new papers, new techniques come out, they often come to Python first. Python is much more useful than Stata and R for general purpose programming. Python has a massive community of developers working on code, so much of the code has already been written. Python can do basically anything. Python has an extremely low barrier to entry for writing code compared to some other languages. You just sit down and then you start writing. It's much easier to learn compared to a lot of languages. And it's the default programming language for machine learning. And that's not going to change. Really, because of the deep learning revolution that we found ourselves in, because now PyTorch and TensorFlow have become so popular, it's going to remain the default programming language for machine learning. Drawbacks: it's computationally slow, not great for scientific computing. I would encourage you to look into something like Julia, C++, even modern Fortran if you're trying to do some scientific computing. There's a much higher barrier to entry than Stata or R. It's much easier to flip open Stata and just run some regressions very quickly. Stata, or Python, there is a barrier to entry, but once you've gotten it, there's a lot of things you can do with it. It's not ideal for certain database tasks. Obviously, SQL is a database killer. And it can cause problems when used without strong understanding. So you need to make sure you're understanding what you're doing, which is a great point of taking this class. In Python, you have different types. You have float, which is a type of variable with floating programming precision, where it's basically like 3.5. You have integer, which is an integer precision, where you have a variable that's just -1, +1, 0. You can have string, and a string is like the text. So if you were to write down what I'm speaking now, You have a string, and then you can have a Boolean, which is true or false. In terms of data structure, you can have lists, tuples, dictionaries, and sets. Lists are ordered, changeable, and allow duplicate values. Lists are indexed starting at 0, and you can add to lists using append and take from lists using remove. List of 1 is the second item in the list. I lied there. List of 0 is the first item in the list because lists index from 0. Dictionaries connect individual keys to values. It allows you to link and create mapping tables, useful creating trees and more complex data structures. Dictive key equals value. Variables are assigned in Python using one equal sign. So if we want to assign value x to true, x equals true, print x, and then you'll get true. Equality is checked using two equal signs. False equals true, that is false. And then you have operators, standard minus, plus, divided by, times. And then this was meant to be x equals y equals false. And then x is not equal y equals true. That should be a standard exclamation point, not a separated exclamation point. Math.ceil gets the next highest integer, rounds up. Math.floor rounds down to the next lowest integer. Math.factorial finds the factorial value. Math.log takes the natural log. Math.exponent takes the exponent. And then randint generates a random integer between two numbers. If statements allow you to perform operations only if certain conditions are met, useful for handling edge cases. If x equals 200, print high, and then it'll print high. For loops allow you to iterate over a set of objects or perform an action a certain number of times. For I in range 10, for I in list, so that will perform an action for every item in the list. While loops do the same, but they perform a task until certain conditions are met. While x less than 200, that should be a less than, x equals x plus 10, print x. Functions start with define and then arguments. Functions have the keyword arguments and positional arguments. Keyword arguments require you to put in like people equals and then Dana, John, Lilia. So it would have a keyword that defines the argument. A positional argument you just put in the right position. Functions allow you to reference different tasks that you do routinely and build more complex routines. To install packages in Python, you add Python to pap, and then you use pip to install packages from the command line. In Collab, you use exclamation point pip to install a package. To use a package, import the package. So now we're just going to do some Python from the Brightspace. So from the Brightspace, I've uploaded some files. Pip install numpy. Pip install pandas. I encourage you all to work along with me. Really, it's important. Like I said, programming is not a spectator sport, so it's important to try and follow along on your own machines. All right, so now this is my introduction to Python. First things first, we're going to import the function that we need. Gonna run these on this from the command line. So import math and then print hello world. In Python, printing is just done by print and then the variable you want to print. Assignment is done with one equal sign, and then you can find the data types by doing type of the variable. And then we have type of I equals int, type of L equals string, type of W equals bool, type of X equals float. So float of J, if you take the float of 1, it's going to give 1.0. And if you take the int of W, if you take the int of a Boolean, it will give 1 if it's true, 0 if it's false. And then we have int of H. Int of H has resulted in an error. Why did int of H result in an error in this code? So what is H? What type of variable is H? That it's not a character. In Python, it'd be called a string. But yeah, exactly, it's a string. So because H is a string, it can't generally be converted to an int. Now, if I did int of 4, that will also not work. So you generally cannot convert a string to an int. They're incompatible types. Python is also case sensitive. So if I do hello equals hello, it will return true. If I do hello equals hello, where some of the characters, oh, sorry. If I do hello equals hello, where all the characters are the same case, it will come up true. If I do hello equals hello, where some of the characters are not the same case, it will come up false. And also remember that variables, Python assigns true to 1 and then false to 0. 1 equals true. That didn't work because we didn't use 2 equal signs. We needed to use 2 equal signs for that to work. Now that we use 2 equal signs, we can see 1 equals true is true. 1 equal false is false. Notice that if we do 1 equals true with lowercase, it does not work because the Boolean true is uppercase. And so in terms of addition and subtraction, you can only concatenate string to string or int to int or float to int. You cannot concatenate string and int. But if you add together 2 strings, here you have a string hello and a string goodbye. You get hello goodbye. If you add together 2 ints, you get another int. And then if you add together a int and a Boolean, you get another int. We also have multiplication and division, and we have modulo. Modulo is basically a remainder. Notice you can multiply a string by an int. You may not be able to add an int to a string, but you can multiply a string to an int, and that will just repeat the string a bunch of times. And then in terms of modulo, yeah, you're taking the remainder. So the remainder of 53 when you divide by 10 is 3. The remainder of 53 when you divide by 9 is 8. So 9 times 5 is 45, and then plus 8 is 53. So an exponential in Python is two times operators, or two different stars. And so you can see that's how you take an exponential. And then the logical operators, you have or. So true or false, what is that going to deliver? What is true or false going to deliver? So yeah, true or false actually will deliver it will deliver false, or sorry, will deliver true, because the logical operator or is if you think about it as a I'm sorry yeah, I didn't mean to make the question mid MD, sorry, MD. But yeah, if you do or that that if you think of it as a Venn diagram, you're saying is either true or false in the Venn diagram. So if the first statement or the second statement is true, it will come back true. This pipe character is just another way of doing or. And then if you have true and false, what's it going to come back as? So true and false. So true or false is true. True and false, though, is only true if both true and false are both true. So what will true and false come back as? Correct, MD. It's going to come back as false. And this is just another way of writing and. You have the ampersand. And then you can do expressions in your logical expressions. And then we have for loops. So for I in range 10, print I. So this is just going to print I from 1 to 10, from 0 to 9 rather, because Python indexes from 0. So this is a while loop. So this is going to do the exact same thing. It's going to do it using a while loop. So now we also can have functions. Define hello world. And so now functions allow us to do something repetitively and repeat one action a bunch of times. So can someone give me a number? Just any number? Let's do 10. It repeats hello world 10 times. And for MD, we will also do 9. And then we can do if statements. So we're going to do 9 again, and then we're going to do 4. So now this does the same thing, but it only does print hello world if I is greater than 5. So with 9, it prints hello world it prints hello world 9 times because 9 is greater than 5. But if we do 4, it doesn't print hello world at all because it iterates 4 times and it sees that I is not greater than 5. So we want to take the square of something. We just take the value times itself, square of 5. Oh, no, sorry. This is not taking the square. This is taking the value raised to itself power. So if we want to take the square, let's do this. Debugging is an important part of coding. You always have to notice what the mistakes are, be very okay making the mistakes, and then be able to fix them. It's always important to test your code to make sure it's doing the right thing and to figure out how to fix it when it's not doing the right thing. So is it a square? So this just tests whether or not it is a square. Then this is a list. So I just create an empty list and then I append the name Harry. And then I create a second list of names. Print the second list of names. And then I add the list together. So when you add the list together, you get a list that is the second list concatenated on the first list. And then if we extend the list, we actually just get the same thing. So if we remove Pokemon, what's this going to do? Does anyone know what this is going to do? Or will this code even run as I've written it here? The code is not going to run. So Pokemon is not defined. Oh no, we have an error. Let's try putting it in string. It's still not going to run because the value is not in the list. But what if we capitalize the P in Pokemon? Now it runs. So it's important to remember that Python is case sensitive. So this is a data structure called a tuple. So a tuple is basically a ordered set of objects. But unlike a set, it can have multiple of the same objects. And then if you want to figure out how many objects are in a tuple, you just do print len of tuple. So it can have all sorts of data structures inside. This is a dictionary. It allows you to map objects from values to keys. So if we do print this dict of brand, we get Ford. If we do another dict, we can put in all sorts of types of values inside of it. So it doesn't just have to contain one singular type of value. We can also have what's called default dictionaries. And what default dictionaries do is allow you to create a dictionary that returns a standard reply when the object is not present. So in this case, we're defining not present as the standard reply. So A is present in the dictionary, B is not, or B is, C is not. So when we type D of C, we get not present. So here we do default dictionary of ints. And so now when a variable is not present, it's going to give 0. So now it's going to start off with, so we just initialized D, so it doesn't have any values in it. So what is this dictionary going to do? What is this dictionary actually going to do? This default dictionary. So it's going to initialize any values not in the dictionary to 0. And then it's going to add 1 if it for each item in the dictionary. So what do you guys think it's going to do? For sake of time, I'm just going to run the code. What it's going to do is it's going to create a dictionary with the number of times an object shows up in the dictionary. So this is with sets. Sets are like lists, but objects are unordered and objects are unique. So if I put in this set equals apple, banana, cherry, apple, and I print this set, it's just going to give me one apple. And it's not going to retain the order. So this is an important feature of sets, is that the set of something throws out identical objects. And you can also have sets with different types of values. So recursion is another idea in coding that's very important. Who knows what recursion is? So recursion is this idea in programming where you use a small problem to solve a bigger problem. So basically, you have the return of a function be itself. So you're taking the factorial of n. So factorial, if you recall, is a number times every number before it. So if the factorial of 0 is 1, and then the factorial of every other number is the factorial of itself times every number less than until you hit 0. So here we do factorial of 0 equals 1. And we do the factorial we return is n times factorial of n minus 1. So there you have it. That's factorial. And here, the Fibonacci sequence can be calculated in much the same way. If n equals 0, the Fibonacci sequence equals 1. If n equals 1, the Fibonacci sequence equals 1. And you can calculate any Fibonacci number by summing the last two. And so this is the important part of a recursive argument, is that you have a default return at the minimum value, and then you have a recursive step. So you have something that returns if it's not the minimum value, and then it decreases till it hits the minimum value, and then it returns something. You want to make sure that your function always terminates. You don't want your function to be running forever. So Fibonacci of 3 is 3. Fibonacci of 10 is 89. So that's a way to calculate Fibonacci's. So both those use recursion, and both those are probably something you learned on the first computer science class you ever took. That's really slow. Why is it really slow to be using recursion to solve a problem like that? Why do we want to avoid recursion in those scenarios? Recursion in those scenarios is memory intensive, and it's also really slow. So what we want to do instead is use, it's memory intensive, it's also really slow. What we want to do instead is use dynamic programming. So now what we do is we, instead of recalculating every time, we create a dictionary with the values we're interested in, and we use that value with every other time. So now, for I in range 1 to n plus 1, instead of doing the factorial by taking a recursive step, we're basically creating a dictionary of factorials, and we're multiplying through the factorial. And if you notice, does anyone know what the factorial of 5 actually is? if you're working this code throughout with me, you'll have it right in front of you. What is a factorial of 5? 120. And the 8th Fibonacci number, I believe, is 32. 21. So close. So that's dynamic programming in a nutshell. Very valuable way of solving problems, particularly in economics. So this is file IO. In this class and in just general programming, you're going to be dealing with a lot of files. So sometimes you're going to want to know what working directory am I in. So you'll know where your files are going. This is my working directory. Sometimes you'll want to change your working directory. So you can just type in your working directory. That's not going to work because I'm not in a working directory. So what I have to do is I have to type in my working directory. Now, this is not going to work. And this is not going to work because of a Unicode error, because the slash has a particular meaning in Python. So I have to do this. Another option is to, instead of changing the directory in your program, you can have the, this sets the directory to this directory. So instead of setting the directory in your program, you can set the directory via the command line. And then here, this is how you write a CSV. This is how you read a CSV rather in Python. I haven't put a CSV in that directory. And then this is how you write a CSV in Python. So we've written a CSV called names, and then voila, we have first name and last name in our CSV. So in error handling, you might sometimes want your program to work even, you want your program to ignore times in which it won't work, and then instead move on to times in which it will work. So in this for loop would generally not work. This for loop would generally not work because you can't divide by 0. But if we run it like this, now it will skip the times when it'd be requested to divide by 0, and it will return can't be done. Actually, let's just do 022. There we go. That gives the behavior I want. So there we go. Anytime it was supposed to be dividing by 0, it will return can't be done. So finally, in this introduction to Python, we have classes. So a class in Python is a way to create instances of a particular object. So you have class car, you have class attribute, and then you can have a constructor. The constructor allows you to give objects to the class. And then you have an instance method, which allows you to have a brand, model, year. And so now we can have car. Car is an instance of class. Classes are really important for deep learning in particular. And so if we do car1, you'll notice it's a class, and then the class has attributes. So if I do car1 dot brand, it goes back Toyota. So classes allow me to provide a car1 of year. So they allow me to create a way of handling instances and creating instances. So I can display info, and I can run a function about the class. So this function is drive. So it's a method. And then what it does is it prints self.brand, self.model is driving. And then we can count, we can print facts about the cars, and we can print the total number of a class that are instantaneous. And then we can have a class called an electric car. This is something called inheritance, where inheritance means that we create a class that has all the characteristics and is a subclass of the class car, but it also has other characteristics. Like here, we have battery capacity. So Tesla is a version of an electric car. And so now Tesla Model S is driving silently with a 100 kilowatt hour battery. So that was a really quick, probably very introductory, I'm sure I bored all of you, introduction to Python. Now we'll move on to introduction to pandas, but before then, I'll wait to see if anyone has any questions. Does anyone have any questions before we move on? Seeing none, we'll move on to the quick pandas intro. So I'm going to skip the PowerPoint for now. Pandas is a really great way to deal with data. It really allows you to work with a variety of objects called data frames. And it really is a great way to recreate R in Python. So you can deal with data from Excel or CSV pretty much natively through pandas. So to create a series, you just do pd.series, and to create a data frame is a combination of several series. You do pd.dataframe. So when you do head, you view the first few objects in a data frame. You do the tail, you do the last few objects in the data frame. When you do df.info, you're provided with the information about the data frame. Let's say I just wanted to view the first object in the data frame. I would just do 1. If I want to do the first 4, I would do 4. Notice Python indexes from 0. And then if you have to describe, it will provide descriptive statistics by each column that is numerical. There was only one numerical column here. If you do print d.data types, it will print the data types. I can also change the data types. Here I can change age to type float. So I can select a certain amount of data by doing df and then of, and then the name of the column. So here I've selected the name, and here I've selected the name and the city. I can also index. I can choose the first, I can choose locate and ilocate. So the difference between locate and ilocate is that ilocate uses an index, and locate just goes with the natural order of the data frame. You can also choose greater than and less than to get certain parts of a data frame. So now I can select ages greater than 30. So that gets Peter and Linda. And now I can set an index. So if I set the index of name, that allows us to choose a default index, which now these are indexed by name. If I want to get rid of those that index, I do reset index in place is true. I'm going to stop right here for a moment, see if anyone has any questions. Just make sure Is anyone having trouble following me on their own machines? All right. Uh, Having seen no questions, I'll just keep rolling. Uh, so there's a data cleaning. You can check for instances of null variable where, in this case, all the variables are there. You can also fill a variable that is null with its mean here. You can choose a way to fill empty objects with a rule. Sometimes you want to drop null values with data. You can also remove duplicates. I'm sharing my screen, right? Good, good. Just want to make sure. You also remove duplicates using pandas. So really the benefit of pandas is it allows you to automate a lot of the tasks that would take a very long time to do. You had to do them manually in Excel. You can rename columns and index. I hope you're all following along. So now I've renamed the age with years. And then you can apply functions to the data frame. So here I'm going to sum up the data frame. And notice, funnily enough, when this sums up name, it just puts the names together. And then when it sums up years, it adds up all the years. I can also perform a lambda function, which allows me to do a particular thing to all of the objects in the function. So here I square all of, or here I multiply them all by 2. And then I can group by function. So this will allow me to take the mean of ages in a particular city. So I group by, and then I take the mean. I was going to explain how to fix this error, but I think I'm just going to move on for sake of time. I can also do what's called a pivot table, which allows me to aggregate the number, the age in terms of years for a particular city, and it allows me to aggregate much like how you'd take a pivot table in Excel. You can join together and concatenate different data frames using concatenation and using join and append. So here we're concatenating, which means we're putting the data frames together. You can also merge 2 data frames on a similar key. So here we have this key, and then we're going to create a data frame that has 3 columns from 2 data frames, each with 2 columns. So look at that. We've combined based on the key to have columns key A and B. You can also work with date time in pandas. So we have a date here, and then now we convert it to date time, and then we get key parts of the daytime. We get the month, we get the day, and we get the year. And then I haven't put any files in here, but you can get a data frame directly from CSV, directly from Excel, and you can also write a data frame directly to a CSV and directly to an Excel. So Python really allows us, you need to use OpenXL with write to Excel, but Python really allows us to work natively with our data. Right here, I need to import a package. It's telling me I haven't. So what I do is I import matplotlib.pyplot as PLT. So it's telling me I haven't installed Matplotlib. So what I do there is I do pip install Matplotlib. And then it won't use it in the same session. So I have to start a new Python session anytime I install a new requirement. So I do Python, and then I run up until here, and then magically uh, uh, so plt.show. So we're gonna move on from that. Sorry about that. But that allows you to create a plot in Python, and then you can also integrate pandas with sklearn. I've not installed sklearn, so we're just gonna skip that part. This is a relatively new computer. So now we're going to run through the visualization and then some basic statistics with Python. And then I think I'm going to let you guys loose. I ran this on my other computer, so it doesn't look like I've installed all of the required modules. So I just want to make sure I install them. Pip install Plotly. So this is also a good time to install these on your own computer if you've not yet. So hopefully you're running along with me and you install these right now if you need to as well. So I'll run the parts of the code that are not dependent on Plotly right now. Python. We create a basic create a basic create a basic line plot using matplotlib. So this using np.linspace and np.sign to create a basic line plot. So here is a line plot with a sine wave. And then we can use Seaborn to create a better plot. This is a basic Seaborn plot with a regression line. And here we have it, a seaborne plot, the regression line that creates a nice little plot there. Seems like Plotly's finished downloading, so we can run some better things. So here's a line plot with Plotly. Plotly is really cool as it allows dynamic visualizations. So here is a line plot with Plotly, and you notice you can directly interact with the visualizations. And then we can create a scatter plot with Plotly Express using the iris dataset. Create this scatter plot right here, and then lovely enough, we have colors and we have the data set annotated so we can see the scatter plot. We can also visualize a confusion matrix using Matplotlib. It needs me to have sklearn, which I don't on this computer. So I'm going to skip that. Let's create another application using Plotly. So allows us to create, Plotly is very cool because it's dynamic and allows us to create dashboards and 3D plots if we want to. And then finally, I'll show so this is another example of what you can do with Plotly. So this is a chloropath of a particular district in New York City. You can see it annotated, and you can see particular parts of the population annotated by population. I also uploaded the statistics info, which I'll run through right now. So we have an example data set, and then you can use np.mean to take the mean of the data set. You can then use np.median, take the median, and you can use pd series.mode, take the mode, np.var to take the variance. Just look through this on your own if you want to. I'll just run it all now, show you what it does, and then if you want to, you can. So this provides a histogram of a randomly generated normal distribution, and this provides a density plot, and then this provides a box plot of some data. So I think we're going to end it there tonight. I promise the future recitations will go more smoothly. Does